Hello, in this video we're going to talk about inverse functions and continuity of inverse functions. So there are some very interesting theorems that we're going to prove, and this allows us to create more continuous functions. First, a couple of definitions. So we say a function is one-to-one if whenever f of x1 is equal to f of x2, then f x1 and x2 are the same. Second, the definition of inverse function, and these two definitions really do not have anything to do with the calculus. They are definitions that you have seen in pre-calculus and more specifically in an introduction to proof class. When f is one to one, its inverse denoted by f inverse is the function from f of d, from the image of f to d, satisfying f of x equals y if and only if f inverse of y equals x. So next few definitions are about increasing and decreasing functions. Consider the function from d to r. We say f is increasing if x less than y implies f of x is less than or equal to y. This one is called increasing. Decreasing is the same except that the inequality is flipped. Strictly increasing means it is increasing, but it is also one-to-one. So in other words, if x is less than y, then f of x is less than f of y and not less than or equal to. So the difference is between less than and less than or equal to. And strictly decreasing is also defined similarly. So these definitions are quite similar to definitions of increasing, decreasing, strictly increasing, and strictly decreasing for sequences. And similar to sequences, if a function is either increasing or decreasing, we say it is monotone. And if it is either strictly increasing or strictly decreasing, we say it is strictly monotone. So these are similar to sequences. However, note that here we are dealing with real numbers, and we cannot just check f of x is less than f of x plus 1. This is one of the common errors that I see. When students try to show f is increasing, they show f of x is less than or equal to f of x plus 1, which is obviously not necessarily, it doesn't necessarily imply that the function is increasing. So you will have to show that if x is less than y, then f of x is less than or equal to y in order to show a function is increasing. Okay, so the first theorem. This one is a very basic theorem. Again, this is not really a theorem from real analysis or advanced calculus. It is more of a theorem from introduction to proof class. So it doesn't really have anything to do with continuity or any concepts of real analysis. Any strictly monotone function is one-to-one and thus has an inverse. And the reason is, if you have a function that is strictly increasing or strictly monotone, then it must be one-to-one, because you cannot have f of x equals f of y unless x is equal to y. So let's suppose f is strictly increasing and f of x is equal to f of y. If x were to be less than y, then since f is strictly increasing, f of x would be less than f of y, which is a contradiction. Similarly, x greater than y is also not possible. Therefore, x must be equal to y. And that means I deduced from f of x equals f of y that x must be equal to y. Thus, f is one-to-one. And if f is one-to-one, then it must have an inverse, as we discussed earlier. Okay, So let's now move on to a theorem that is more in line with what we have been talking about. So let me tell you before I get to the main theorem, let me give you an example. But let me tell you what the main theorem is for today. The main theorem is dealing with the inverse functions. So the main theorem is theorem 4.11 that shows if you have a function from an interval, the domain must be an interval, and the function is strictly monotone, then its inverse is continuous. So this is the main theorem. The proof is a little bit complicated. So what I'm going to do is I'm going to prove this theorem for a specific function f of x equals x cubed, and then we will get to the proof of this one. So before I get to the proof of that theorem, we will talk about this theorem for a specific case. So I have a function from R to R, f of x equals x cubed. We know this is continuous and bijective, and we want to show that it is its inverse is continuous. Okay, so the fact that it is continuous is clear because it's a polynomial. So f is continuous since it is a polynomial. F is onto by an example. This is an example that we did right after the IVT, intermediate value theorem. F is 1 to 1 by the previous theorem since f is strictly increasing. By properties of inequality, we know x less than y implies x to an even exponent less than y to the same odd exponent less than y to an odd and of course positive exponent. We know that. So that means f is strictly increasing, which means it is 1 to 1. So this function is in fact continuous and it is bijective. We want to prove its inverse is also continuous. So the inverse of this function is what we know in pre-calculus. You have learned inverse of function x cubed is the cube root of x. So it's the x to the power of 1/3 or cube root of x. Now, in order to show cube root of x is a continuous function, what we need to do is to show, by definition, that if a sequence approaches a point, then f inverse of that sequence approaches f inverse of that point. So let's start with some real number x naught, and let xn be a sequence that converges to x naught. So what we're trying to do is to show f inverse of xn approaches f inverse of x naught. So let's simplify things a little bit by denoting that sequence by yn, f inverse of xn, and the other one by y0, f inverse of x0. So this means xn would be f of yn, which is yn cubed, and x0 would be f of y0, which is y0 cubed. So let's summarize this. Therefore, we know that xn approaches x0, which means yn cubed approaches y0, and we'd like to prove yn approaches y0. We know yn cubed approaches y0 cubed, and we want to show yn approaches y0. So this is now, to summarize this, this is what we're trying to prove. Yn cubed approaches y0. We want to show yn approaches y0. Okay, so let's see what we need to do. So we're going to do the work on the right, and we're going to write down the proof on the left. And I always use a different color for the scratch work. Okay, so the objective is yn minus y0 is less than epsilon. This is the objective. This is what I'm trying to prove. If I'm trying to prove yn approaches y0, I would need to prove yn minus y0 is less than epsilon for large values of n. Okay, so let's rewrite this one. If you open this up, we get yn is less than y0 plus epsilon and y0 greater than y0 minus epsilon. Now, since I'm dealing with yn cubed and y0 cubed, it would make sense to cube this to see how we can relate this with what we are given. So this is what I'm trying to prove. Because everything is increasing, the cube function is increasing, these two are equivalent. Is strictly increasing, in fact. Okay, but what I know is this. I know yn cubed minus, so this is what we know. Yn cubed is approaching y0 cubed, which means yn cubed minus y0 cubed can be made less than any arbitrary delta. So if you take some delta positive, you can make yn cubed minus y0 cubed less than, in absolute value, less than delta. That one we can do. If we rewrite this one, we will get y0 cubed plus delta and y0 cubed minus delta. So if I make sure that delta is less than both this and that, both the distances here, then I would be done. So in other words, what I would like to do is I would like to make sure this is less than or equal to y0 plus epsilon cubed and y0 minus epsilon cubed to be greater than or equal to y0 cubed minus delta. If I make sure both of these two are valid, then I would be able to solve the problem. The first one gives me delta is less than or equal to y0 plus epsilon cubed minus y0 cubed. And the second one tells me delta is less than or equal to y0 cubed minus y0 minus epsilon cubed. So I would need both of these. And of course, y0 cubed, y0 plus epsilon cubed minus y0 cubed is a positive number, and so is y0 cubed minus y0 minus epsilon cubed. If I take the minimum of those two, then I would be able to achieve what I want. Okay, so let us go ahead and prove this now. So we started with assuming that yn cubed approaches y0 cubed, and now we want to prove yn approaches y0. So let epsilon be positive. Set delta to be the minimum of y0 plus epsilon cubed minus y0 cubed and y0 cubed minus y0 minus epsilon cubed. This is what I had down here. y0 cubed minus y0 minus epsilon cubed and y0 plus epsilon cubed minus y0 cubed. Note that y0 plus epsilon cubed is greater than y0 cubed and y0 cubed is greater than y0 minus epsilon cubed. Thus delta is in fact positive. So this delta is positive. Now I would like to use the fact that yn cubed minus y0 cubed can be made less than delta, and that can be done because yn cubed approaches y0 cubed. So let's get to that. So by, I'm gonna call that, I guess, star. By star, there is some natural number n such that for every natural number n, if n is greater than or equal to n, then the distance between yn cubed and y0 cubed is going to be less than delta. So this means yn cubed is less than y0 cubed plus delta and greater than y0 cubed minus delta. Now if you look at y0 cubed plus delta, that is less than or equal to y0 cubed plus delta was minimum of y0 plus epsilon cubed minus y0 cubed. So this is y0 plus epsilon cubed. If you look at y0 cubed minus delta, this is greater than or equal to y0 cubed minus delta was minimum of two things, one of which was y0 cubed minus y0 minus epsilon cubed. And since I have a negative sign in front, when I look at the inequality, it would be flipped. So this is y0 minus epsilon cubed. If you combine these three inequalities, you would get y0 minus epsilon cubed is less than yn cubed less than y0 plus epsilon cubed. And finally, we will get, by properties of inequality, we are going to get yn is greater than y0 minus epsilon and y0 plus epsilon, which is to say yn minus y0 is less than epsilon. So we showed for every n in n, if n is greater than or equal to n, then yn minus y0 is less than epsilon, and therefore yn approaches y0. And this is exactly what we wanted to show. So thus f inverse is continuous. Okay, so now in a similar fashion we can prove this, the objective. We can prove that if you take an interval and if you look at a strictly monotone function, whether it is strictly increasing or strictly decreasing, then its inverse is always continuous. In a similar fashion we can prove that. Okay, however, instead of doing that, we are going to prove something a bit stronger. We're going to prove a theorem that is stronger than this, and then we're going to actually obtain the main theorem 4.11 that we discussed at the beginning. Okay, suppose f from D to R is monotone. If its image is an interval, then f is continuous. So let's see what the theorem tells us and why it would make sense. We have a monotone function. Notice that this one is not necessarily strictly monotone. It could be just any monotone function. But what we do know is that the image is an interval. So the image could be some interval. It could be a closed interval, open interval, bounded or unbounded interval. Any of these kinds of intervals is okay, as long as it's an interval. If the image is an interval, then f is continuous. So the domain may or may not be an interval. The image would have to be an interval. In order to show f is continuous, I will have to show, if I take a point x0, it would be continuous at x0. So the idea is, if you take a sequence approaching x0, then f of that sequence must approach f of x0. Why? Because if there is a jump, if you go from here, like this is your function, if you were to have a jump, then your if you had something like this, if there were to be a jump at some point, then there would be a gap here, and this gap is not okay, because if you have a gap, then the image cannot be an interval. That's the idea. That intuitively, that's why. So if you're always going up, the only way you can have the points of discontinuity is if you have a jump. And if you had a jump, it would have to be a vertical jump, which means that would be problematic, because then your interval would be, your image would not be an interval. So that's the idea of why it is true. Now, making that more rigorous and writing down the proof proves to be a little bit more complicated. So let's go ahead and write down the proof for this one. Okay, so the first step of the proof is clearly, in order to show it is continuous, is clearly to show if you have a sequence approaching a point inside D, then the functional value of the sequence approaches the functional value of that point. So we're going to start with let x0 be in D and xn in D be a sequence with xn converging to x0. The objective is to show f of xn converges to f of x0. Now, if f of xn doesn't get close to f of x0, then there's going to be a gap. And then we're going to show that, well, there is a gap, therefore the image is not an interval. So that's what we're going to show. Okay, so suppose on the contrary, f of xn does not converge to f of x0. By an exercise, there is some positive epsilon such that and some subsequence of integers and a subsequence, or in fact a subsequence of xn's, subsequence xnk, such that the distance between f of xnk and f of x0 is more than epsilon. So the distance between these two is large. This is going to be at least epsilon. And then we're going to show that, well, since xn's approach x0, then this gap is never going to be filled. That's the idea. However, since your f could be on either, your f of xn could be on either side, I'll have to take two cases. And by the way, my function is a monotone function, so it could be increasing or decreasing. I'm going to deal with increasing functions first. Okay, so assume f is increasing, and the proof for decreasing would be quite similar. Okay, so now there are two possibilities. Case 1 is f of xnk minus f of x0 is positive, which is and this is greater than or equal to. And case 2 is it is negative. So this would be f of x0 minus f of xnk. So there are two possibilities for the absolute value. It's either f of xnk minus f of x0 or f of x0 minus f of xnk. The first case tells us f of xnk is greater than or equal to f of x0 plus epsilon. Now let's look at what happens. So I know f of xnk is, in this case, it's right here. It's above that. I'm going to show that this region cannot be obtained by any value. Well, first of all, I know there's gotta have to be something in between here. So since f of x and k is greater than f of x0 plus epsilon over 2. I'm sorry, this is yeah, and that's greater than f of x0, and f of d is an interval. There is some point in d such that f of c, so f of d is an interval. These 2 points are obtained, are inside f of d. Therefore, this thing in between must also be a functional value. So there's some c in d such that f of c is equal to f of x naught plus epsilon over 2. But that means if I look at f of x and k, that's greater than f of c, which is greater than f of x naught, which means x and k is greater than c greater than x naught. So that means x and k x and k minus x naught is more than c minus x naught, which is a positive number. This distance is less than this distance. C minus x naught is a fixed number. So that means x and k cannot approach x naught, because x and k minus x naught is more than something that is positive, more than a fixed positive number. And we're going to do something similar here. So this one is f of x and k. I'm going to write that down completely. This implies if I look at f of x0 minus epsilon over 2, that is clearly less than f of x0 and more than f of x and k. And again, since f of d is an interval, there is some, I will call that d, inside d such that f of d is equal to f of x naught minus epsilon over 2. These two are inside f of d. Therefore, this guy, which is in between them, must also be inside f of d. And that means f of x0 is greater than f of d greater than f of x and k. But f is strictly increasing, so that means x0 is greater than d greater than x and k. So this means in that case, the distance between x and k and x0 is greater than the distance between x0 and d. So therefore, the distance between x and k and x0 is greater than the minimum of these two, minimum of x0 minus c and x0 minus d. In one case it was more than x0 minus c, and in the other case it was more than x0 minus d. And this is a positive number. Thus x and k does not converge to x0. And this is a contradiction. Because xn converges to x0. And this contradiction shows that f of xn must converge to f of x0. Okay, so let's recap what we did. We wanted to show f is a continuous function. We started with a sequence xn that converges to x0, and the objective was to show f of xn also converges to f of x0. What we did was we assumed f of xn doesn't converge to f of x0. Then we used an exercise to find a subsequence that the difference between f of x0 and f of xn is greater than or equal to epsilon. And then we use that to show that there is a gap that f of x and k is gonna have to is not gonna be able to approach f of x naught. There's a gap between f of x and k and f of x0, and we use that is where we use the fact that f of d is an interval, and we had to take two cases. Now this was for the case when f is increasing, and when f is decreasing, the process is identical, nearly identical. Or you could look at negative f as a function that becomes increasing and go from there. Okay. As a corollary of this, we can see that suppose if the domain of a function, a monotone function, is an interval, then f is continuous if and only if its image is an interval. So there are two directions. This is if and only if. If it is continuous, then the image is an interval. This follows from the IVT. So this is a theorem that follows from the IVT. So we proved this before. Right after IVT, we proved this theorem. The converse is if it is monotone and the image is an interval, then the function is in fact continuous, and that's just exactly the theorem that we proved, theorem 4.10. So this completes the proof of the corollary. Okay, so next we are going to get to the main theorem, and this is a very important theorem that we'll use, and next time we'll talk about some more examples on this theorem. Let I be an interval and let f from I to r be a strictly monotone function, then its inverse is a continuous function. So the inverse of a strictly monotone function is in fact continuous. So in order to show a function is continuous, if it is monotone, all I need to do is to show that the image is an interval. So if you look at f inverse, since f is strictly monotone, so is f inverse. Okay, this is again an exercise in introduction to proof. If f is strictly increasing, then f inverse is also strictly increasing. If f is strictly decreasing, f inverse would also be strictly decreasing. So this is not very difficult to prove. So we know that f inverse is strictly monotone. Now if you look at the image of this, f inverse of f of I, this is exactly I. Again, this is an exercise from introduction to proof, which is an interval. Therefore, by theorem 4.10, f inverse is continuous, because theorem 4.10 told us that if you have a function that is monotone, these are the two conditions, monotone and its image is an interval, then it would have to be continuous. So two conditions, it is monotone and the image is an interval. And for this theorem, we proved that in fact the image is an interval because the image is I. The image of f inverse is the domain of f. Domain of f is I. Therefore, f inverse of f of I is I. And it is also a monotone function because f is strictly increasing, so its inverse would be also strictly increasing. Okay, so that brings me to the end of this video. So if you're interested in continuing with this, feel free to subscribe the channel, and I will see you in the next video.